Evan Sheely is with us today as our sponsor with Secor here. Come on and tell us a little bit about what Secor does and how anybody on the call can get a hold of you and find your services.
Yeah, no, Alan, thanks for the introduction and thanks for having Secor as a sponsor. We're always thrilled to team up with you guys in the Alliance. It's always great to educate the public on the advantages of polyethylene pipe. I've been with Secor for over a dozen years now, and Secor is a very large distributor of HDPE pipe and a manufacturer of fabricated HDPE fittings. We'll also have my colleagues Mark Christensen and Chris Waite on the call today as well, helping out with the panel and sharing their knowledge on today's topics. So, our contact information, I believe, is at the end of the conversation, but you can always find our information at secoronline.com. That's Secor, SECOR online.com if you want to reach out in the meantime.
Awesome. Thank you very much for donating the Mark and Chris for us too. Those experts really make all of this better and sharing your expertise as well, Evan. So we really appreciate your being here and also sponsoring this content so that way we can reach out and provide it to everyone there. So here's today's speakers, Stephen and Chris. You want to come on and introduce yourself to us and tell us who you are and who you work for.
Yeah, hey, good morning or good afternoon, I guess. I'm Stephen Boris. I'm with Pipeline Plastics. I'm the Vice President of Engineering here. Been in polyethylene pipe for 30, God, I hate to say it, 35 years now. Started with resin development, pipe manufacturing, Plastics Pipe Institute, back to pipe manufacturing, and I really enjoy educating and spreading the word on polyethylene pipe.
Awesome.
I'm Chris Waite with Secor. I branch manager up in Wyoming, work in the Wyoming Dakotas area. I do outside sales, I do field work, I do just about anything I have to do, along with helping the Alliance educate people alongside Stephen and Alan.
Awesome. So stay on for just a second. So these two fellas, and part of our industry is always like this. We kind of like each other. We also are very passionate about what we do. So Stephen and Chris attended what we call a PE Alliance showcase not too long ago, and we had a caricature made. And then they brought me this idea that they needed to have an engineer and a constructor or contractor. Chris didn't quite call himself that, but the humility is certainly there in that function. And they just had an absolute blast developing this idea for us as to what is actually different from a design intent all the way to what in the world are we putting in the ground. And so that's kind of the genesis of what we're based upon here. And I personally love the character here, Stephen. Chris, I don't know if you want to elaborate a little bit about that, but this is the humility in itself.
No, I agree with you. It was a lot of fun. It was actually Chris's idea. He grabbed me and said, "Hey, come on over here. Let's get our drawing done." And he gave it the title, and I thought, "Oh, come on. I'm not sure which one I was going to be." So he let the guy who drew it to figure that out.
All right. So here. Today's bench force is Dan Landy, Ian Deathloff, and then also John Stevens. Brian Swanson has also joined us on the call as well. So we've got a pretty good deep bench. Mark Christensen will be operating in that function as well. If you haven't attended a Alliance for PE Pipe program before, what we've got going on is a parallel track underneath the main content. And that parallel track, you can type in any question that you want in Q&A, and then there'll be a live person. In this situation, 5 live people behind the scenes ready and willing to type that answer for you. And so everybody's here to be able to provide that live answers to your questions. So don't hesitate. You do have to type it into Q&A instead of chat. That's a way for us to track it and then also be able to share the answers with everybody that's there. If you're here primarily because your boss told you to or to get CEU credits, there'll be a survey at the very end of this presentation. You answer the 4 or 5 questions that are involved in that survey, and that's the quickest possible way for you to be able to get your CEUs through that process. Take a screenshot These are the contact names and the individuals that are here and part of this program for us. We're very, very happy to talk about all things that we presented today, including any other external questions that you have about high-density polyethylene. Love to share our stories and love to talk to you about your particular project as well. So I'll give a couple of slides of a primer here, and then let Stephen and Chris kind of sort of take it over for us. The question really becomes, how do we go from this piece of paper that's a specification that essentially is included in, part of the bid documents, which could be voluminous, that a contractor receives and is bidding on, or a subcontractor or distributor if you're providing a particular item, to the video that you'll see on the right here. How do we move from one to the other? And then more importantly, if something gets messed up along the line, how do we translate exactly what went wrong, what we're going to put into practice, or what have you? The Alliance does have this excavation, backfill, and compaction for utilities. It doesn't necessarily directly spell out the video that you're seeing on the right here, but everything that's discussed in the verbiage in the specification is actually done in practice in the video that you're seeing. There's a solid foundation, which is free and clear of rocks or other things like that. There's a bedding at the bottom of this trench, which happens to be a soft amount of soil or other things to be able to receive the pipe. And then once they push the pipe into the trench, they'll come back through and put backfill and compact that backfill in the appropriate lifts. A lift becomes, less than 12 inches of backfill that can be compacted, because you can't compact typically more than that. So this is how we translate from the text all the way over into the video that you've seen in that scenario. There's a lot of things that we have to address. Anyone on the call here that's done construction before knows that any number of these items can go potentially wrong in the field, or right, once we've done it long enough and know exactly how to do it in that manner. So how do we take all of the design considerations, the operational parameters of the pipe system that we're putting into place, and then know enough about all of these other things that we have to cover during construction? Again, at the beginning, I said we learn more from failure than we do by success. The second that we have a really big screw up that's going to cost a lot of money, we certainly will not forget about that particular compaction or that trench shoring condition that we talked about. We'll talk about a little bit later in this function. So here is flow design and ID matching. We often get compared to a thinner wall pipe because of our thick wall as we go through this. This is a theoretically simplistic scenarios to which we have one pipe, very long pipe, and we're looking at friction loss all across that. It doesn't happen that way in typical potable water distribution systems, collection systems, or force main pumping systems as we go through. There's lots of moving parts and pieces with friction losses around bends or corners or other things like that that we have to consider. Stephen, absolutely.
Yeah, I think this is a really important topic because we keep seeing a lot of misleading information out there. And I think it's really important people understand the hydraulic models that go across this. It's so easy just to say, well, I need a pipe with a certain ID, end of story. Unfortunately, it's not that simple. There's a lot of different things that go into it, and every material needs to be looked at differently on those terms. So all we ask is that you properly look at the attributes of every material and design for their optimum benefits. I mean, it comes down that simple. Let's not oversimplify it to where you're not giving a proper design based on every material property. That makes sense?
Absolutely. Keep going, Steve.
All right,
Try to
we're
answer
going to
this
keep
question.
going. Now I jumped into it now. So, okay, so what defines the hydraulics of a pipe? We all know that it has to do with the inner surface, the ID, the cross-sectional flow, and mostly the frictional factors that are developed over that. So it has a lot of different factors and functions to it. We can see from the equations here the things that go into it to give you overall flow capacity. But for polyethylene, where we have some advantages. Polyethylene is a very smooth interior surface, so you get very smooth flow. You don't get a lot of frictional losses, and it stays that way over the life of the system. That's a very important point. Not all materials do that. So you need to make sure you're sizing your system not just for flow now, but what for flow is going to be in 10, 20, 30, 40, maybe 50 years from now. And I've really never, well, not many piping systems go down in volume need over the years. They always go up. And so how do you get more flow through a older pipe? Well, you got to increase velocity. What happens when you do that? A lot of things you got to take into account when you increase velocity in most of the older systems. With polyethylene, you can increase the velocity. We can get into some of that later on and not have the other effects that come along with it, especially with an aging system. So as
So-
Alan would say, oh,
Go ahead. No,
Nope.
you got it. You got it.
as Alan was saying, there's a lot of different things that go into it, hydraulic modeling. This is a typical table you will see out there, 24-inch, 10,000 feet, a little under 2 miles of pipe. Oh, just lost my screen. There we go. And this is what you might see some of the piping organizations put out there. And they say, all right, well, here's a apples for apples comparison, but unfortunately, it's not really always apples for apples. I mean, this is a snapshot in time that you have to take into account. And there's a lot of other factors that go into it as is. If it was that simple, engineers wouldn't be doing their job. So there's more to it than just this on a hydraulic model.
The thing I want to bring up with you there, Stephen, is if we can jump back to that slide real quick, Alan. People don't look at this. They look at this at the beginning of the project. But if you look at that C factor later on down the line with ductile iron pipe, steel, any of that stuff, that C factor starts going down over time. Where polyethylene maintains that C factor through the entire life of that piping. So as that buildup happens in there and the tuberculation starts happening in there, your flow rate's going to go down over that. And that's why Stephen's saying that you have to design that system for 50 years out to keep that tuberculation and the buildup inside that pipe, because it's gonna take the ID of that pipe down, so you're gonna get less flow over time.
Yeah, exactly. And then, you have to look at how these are designed as well. I mean, so we'll talk about pressure class a little bit later on, but you see just this comparison, they take a very favorable look at some piping products and a very unfavorable look at other products, and they try to compare those. They're not really apples for apples. In this scenario, you probably wouldn't need a DR11 polyethylene, DR13.5, or even a DR17. If a PC200 ductile iron will work, then probably a DR17 polyethylene will work. So you have to take a look at the attributes of each material and see, all right, how do I properly design and optimize these designs for whatever customer or end use you're looking at. And then, of course, we have pipe. We're a pipe manufacturer. We like pipe, but we know that pipe does not make a piping system. You need all the other components that go with it. So you got to have all the valves. You have to have the fittings. You have to have changing of angles in many cases. So you got to have the 11s, the 22.5, 45s, 90s, the T's, the elbows, the Y's. They all add frictional forces to this system and are going to play a part, probably as large or maybe even a larger part of the flow models of any piping system that you have out there. So the pipe, don't get, I guess looking at just one part of it, making sure you're taking them all into account. So the one thing about polyethylene, though, is you look at these hydraulic models, and Alan's really good on this one here, showing the differences. Is with polyethylene, there's a lot of fittings you don't need that you need for other things. 11.5 or 11.25 and 22.5 degree bends are really very rarely needed in a polyethylene piping system because it has the flexibility to deflect around those if you have the proper amount of right of way. But it does have a very tight bend radius compared to other products. So you can eliminate many of those, as we saw in some of the opening videos on these canal enclosures. I remember talking with Mr. Toy on that earlier on, and he was very skeptical that he would be able to eliminate those fittings. But you saw here how successful he was. So that can't always be the case with other legacy materials. So again, it's not always a clear apples for apples comparison. Would you say that's true, Alan?
Absolutely. And a lot of these slides are trying to set up an ID matching argument that is only really answerable by a complicated hydraulic model that is included for the distribution systems. We've had a couple of questions with people coming out swinging hard on some of these questions, and I love it because it shows us the caliber of the audience that we're really talking to. A lot of times we learn just as much from you as we try to teach in this manner. We've got a really good question to talk about the C factor over time and whether or not there is a slime layer within any type of pipe that builds up. And how do we translate from the paper that we see, which on the onset, if the C factor of 150 came from a lab, as could be potentially indicated by the question, what does it really mean in the field? And we don't know that until we have an extensive hydraulic model to be able to give us what we're looking at. And a couple of the next slides we'll go through to talk about some of that, and then I'll give a real world example of how much water flow comes through a fire hydrant, and is it ample enough to be able to do fire protection as we've seen it. So in complicated hydraulic models, you've seen some of those valves, the impact on it from that table. Here we look at each node. Each node becomes an actual service connection, an actual valve, an actual bend, something of that nature. And then we have to model the friction loss along that particular function. And it's actually rather challenging to be able to take a complicated distribution system, 215 miles, 115 miles, whatever it might be, and then model each particular segment and node with the actual flow through that process. Now, once that hydraulic model is put together, you also have to calibrate the hydraulic model. And you do that by taking measurements and all sorts of things out in the field to see it. We had the blessing to be able to interact live with St. Petersburg at a recent roadshow, and that crew itself loved high-density polyethylene for a lot of the benefits we've already talked about, but put a 6-inch pipe out to a fire hydrant, and one of their engineer staff says there's no way that would be able to provide ample fire flow from the constricted ID. They took subsequent actual flow meter readings from the fire hydrant to be able to prove that it was providing enough fire flow through that process. And then still, we're having some pushback from the engineers to do that as well. So it is not as simple as one pipe ID, not as simple as, a assumed C factor as well, as one of the questioners pointed out in that manner. Now, over time, some of the metallic pipes will corrode. They will have tuberculation within it. You'll also have some biomass and other things that may very well have a degrading of that. But thermoplastics typically do not degrade in that type of fashion over time. Now, that's about all we're going to have for ID matching because there's a lot of other things involved here. So keep going, guys. You're doing great.
Yeah, there's a lot. So here I'll talk about the here, Chris. We'll hit the actual the engineer part and then the actual part. How about that? So you look at the handbook calculations. Calculating thermal expansion coefficients are very straightforward. They're all established. We know what it is. You have a certain delta T, you get a certain delta L, depending on the type of material. That's theoretical. And I know as engineers, we have to take a look at what that potential might be, but we also know that in the field, it's going to be a whole lot less. This looks at totally unrestrained type thermal expansion. It looks at instantaneous changes in the material, and we don't see that in real practice, especially in a buried piping system. You rarely see anything like that. Any type of changes are going to be very slow, can occur over hours, if not days or weeks sometimes, depending on seasonal changes. And these theoretical changes that you calculate will never come to fruition. But again, you can't ignore them. You got to take a look at them and make sure they're taken into account. What do you think about that, Chris?
Yeah, I mean, to simplify what Stephen just said, we just get into the 110-100 rule. If it's above ground, unrestrained, you're going to get 1 inch of expansion or contraction per 10-degree temperature change per 100 lineal feet of pipe. And that doesn't matter whether it's 2-inch pipe or whether it's 65-inch pipe. That calculation goes across the board. It's going to extend longitudinally and latitudinally. So you need to look at all of that, especially if you're doing an above ground situation, doing tie-ins at the end of the line. so on and so forth. Make sure your weather conditions are there to go with that. And I'll let Stephen get into the modulus of elasticity here a little more because he talks about it better than I do.
One of my favorite properties. The modulus elasticity for plastics. Took me a long time to understand this compared to, because we're never really taught this in school, right? We're not taught how do you model or how do you look at properties of viscoelastic materials. Steel, concrete, wood, I mean, all those have very finite properties. So for polyethylene, the established elastic modulus is 150,000 PSI. That's under certain temperatures, certain conditions. So we use that as a basis for our models, and such as our example here. As Chris said, the size of the pipe really doesn't matter. It's going to be the same length of expansion or contraction. And that 150,000 modulus is a short-term modulus. That's something that happens over a couple of minutes. If it's a slower strain rate, if you will, or a slower reaction that takes place, slower delta T, that modulus is going to become lower, and the effect of that modulus is going to be reduced. But let's just say for this example, you got worst case scenario, you get a 40-degree delta T change. What does it take to restrain that polyethylene to keep it from moving? Let's say it's restrained at both ends. All it takes is 700 pounds. On this 2-inch DR11, it takes 700 pounds of force to restrain that polyethylene from moving at all. At that point in time, there's no movement that takes place. Polyethylene's not going to tear itself apart. There's nothing detrimental that's going to happen. It's just going to sit there. If you had the same carbon steel line, you'd need over 8,000 pounds of anchoring force to keep it from moving 3/5 of an inch. In a critical application hooked up to a valve or going through a wall or other kind of housing, that could be pretty detrimental, and you got to really design for that. With polyethylene, you may have the potential for the movement, but the ability to restrain it is much simpler.
Absolutely. It's them numbers down there don't lie, and the amount of force that you get out of the carbon pipes and comparative to the thermoplastics is crazy. How easy it is to restrain polyethylene pipe.
Correct. So again, you look at the theory. The theory gives you a very simple equation: delta L times the coefficient, thermal expansion coefficient, and delta T, and your overall length. Then you have it is independent of size or DR, and the force will then be dependent on the cross-sectional area, of course. So the bigger pipe you have, the more force will be generated, as it would with any material. Let's go from the 2-inch to the 10-inch example. 10-inch DR11 polyethylene pipe. It's going to want to move theoretically as much as 8 inches. In practice, it's going to be much less than that. But again, you only need 14,000 pounds of anchoring force to resist that. That can be done easily with an anchor block, with flex restraints and soils, different things like that, versus almost 200,000 pounds of force that same steel pipe's going to generate. So again, I mean, can you imagine the size of anchor block it's going to take to resist that type of movement versus polyethylene? It's just not the same effect.
All right, here's the where I'll take over for Stephen here. These guys are pulling out 4-inch DR7 pipe. The thing with cold weather is coiled pipe, especially gets affected by the cold weather. It can be dangerous if you're not careful. Don't stand anywhere where that can come around. The biggest thing that I'm going to point out in cold weather, and we're going to go through a few slides of cold weather here, is change the conditions, do not change your procedure. Understand what's going to go on. This pipe stores kinetic energy. You can see when they cut that first band, it just started popping down there. It'll roll out flat, but it is going to have some kinetic energy and going from there. So you got to go nice and slow with it, get it strung out there, and it will lay and relax over time.
Yeah, even in these cold conditions, I mean, the stiffness is going to be higher. Modulus is going to be higher. Go back to that term. But again, it will relax back to its manufactured shape, which is straight.
Yes. So be sure that you're equalizing the system and getting the system equilibrium correct. you want your pipe and your fittings to be the same ambient temperature. You don't want pipe higher than the fitting, you don't want the fitting higher than the pipe. Make sure that especially when you're fusing that stuff, that everything's the same. That way you get the proper melt bead on both sides. You're not getting too big of a melt bead on one side than the other, and going from there. That's gonna make your fusion process a lot easier.
Yeah, that's a good field pro tip right there.
Yeah, generators, and you would be amazed how many people in the field underpower what they're doing. Cold weather affects it, elevation affects the generator output. Be sure you're checking your generator voltage output before you plug your fusion machine into it. Make sure you've got enough power coming from the generator to sufficiently supply your heater, your facer, your fusion machine, the hydraulics and all of that on your fusion machine, because if you underpower those, you're not going to do anything besides tear the machine up over time. And this is a key, especially in the field, using the right tool for the right job. On the left, we've got the poly porter stand where they've got rollers on it. They can prop the pipe up, get it in the machine, keep the alignment. They should be cleaning that pipe back, 4 to 6 feet, keep any moisture out of there. Even the lower rollers on the right-hand side do the same thing, just to keep your pipe aligned and keep everything going. You're going to tint your areas, whatever you got to do there to make sure that everything is protected and you're not getting snow and ice and rain and all that in there. But the same also goes, it's not just cold weather that you need to be doing this. You need to do this in hot weather too. Shield your fusion area, windy areas, you gotta put tarps up, keep the dirt and the dust from blowing in, keep the sun off the pipe. Well, I've been on projects where I've seen the surface temperature of the pipe reaching 165 degrees. It's miserable for a fusion machine operator to stand there around a 450-degree heater plus 165-degree pipe.
It doesn't say that in the textbook anywhere.
It does not. Steven, you want to touch base on this?
Yeah, so back to the thermal expansion contraction coefficient. So this is mainly you're looking at for above ground systems, which, polyethylene is used for very frequently, whether it's a temporary line or a permanent line. The carbon black in there, of course, will protect it from UV degradation for 50 plus years. So that's not going to be an issue. That's why polyethylene is used above ground so much. But because it's black, that's why it gets a little bit warmer than ambient conditions, as Chris said earlier. So there are ways to constrain it. When you do get these temperature fluctuations, day to night, sun to not sun, shade, whatever it might be, there's a number of different ways to constrain that. You can constrain it lateral deflection with expansion loops. You can do an anchored system. You can anchor it on both ends and it won't move. If you have you can do a conventional expansion loop, as you see in the bottom figure, that'll work just fine. The pictures you see here are very common. This is more of a field. We don't show that in our pictures, in our graphics, but in the field, throw a couple of Jersey bears up there, throw some dirt over it every now and then, and that works as a very good restraining system in the field as well. The polyethylene could move on you through these cycles. So as long as you have the proper right of way and you know where you want to keep the pipe from going, it's very easy to keep it from going in that direction.
We're seeing right now, just from morning to afternoon in Wyoming, 40 to 50-degree temperature changes. It may be 25 in the morning and we're hitting 75, almost 80 degrees in the afternoon. So you're going to see a ton of this going on when these guys are laying their right of ways out, especially up north. You're not going to see it as much in the south, but you'll see it in the north where these guys are laying it out. And you notice on that picture in the upper right-hand corner, they have pieces of pipe under that. So as that pipe expands and contracts a little bit, it keeps it up off the bottom of that dirt and lets it actually push through there just a little bit, just to restrain it a little bit.
Keep it going in the right direction. Exactly. So there are calculators for this. So let's say you want to know how many blocks do I need? How many places do I need restraints? Is it 50-foot intervals, 100-foot intervals? What's going to happen at these things? How much deflection will I get? The calculations are all there. All these can be done within the hdpeapp.com calculator, polyethylene pipe calculator, which takes it straight from the PPI handbook. And you can see an example here. I mean, you kind of think, well, is that really going to deflect 48 inches? And yeah, it will, theoretically. Will it be that much in actuality? Probably not, but you're only looking at a strain of less than 0.5% over this. So it's not going to hurt the polyethylene at all. As long as you properly identify it and properly put your supports where they need to be to keep the pipe from moving one direction or the other during these cyclic thermal temperature cycles. Here's how Chris does it in the field.
Absolutely. We'll just loop it around. We've generally got a right of way set up where we can string that pipe out. We can deal with the expansion and contraction. And a lot of times we're not gonna do or have more fused up than we can install in a day. So that makes a difference there too. So a lot of our locations, we can't keep open trench on, so we have to have the trenching closed every night. And so we get enough out there, but you'll see some of this snaking like the picture on the left out in the out on the right of way while you're doing it throughout the day, especially with these 40 and 50 degree temperature swings.
I mean, yeah, these are some great examples of what people do above ground with polyethylene. I see a lot of engineers who aren't familiar with this get very concerned about it. They're like, wow, this is so much more expansion, contraction, movement than I'm used to working with. And they say, well, what's going to happen under these conditions? And you can see it's really not that unusual. It happens every day. You can see the picture in the upper right over here where it's just stabilized on some wood planks as it goes across a canal, or the big manifold structure you have that's in place for weeks, if not months, as a bypass line. These kind of things are very typical with polyethylene, and they don't move a lot. They don't take additional restraints and supports as much as you would think, and they happen every day, dozens of times all over the country.
In-ditch butt fusion, one of my favorite things to not do. But it's a needed necessity in what we got going on.
I was gonna say, I'll tell you all day long. Oh yeah, you could do that. Those guys,
Absolutely.
call up
Stephen-
Chris. He could take care of that for you.
Stephen will tell you you can do it. I will tell you we can do it, but it's not the easiest thing to do in the world.
You
And
can do
see
it.
there's a
You can
lot
do
of-
it.
Yeah, absolutely. There's a lot of moving parts when it comes to an in-ditch butt fusion. You got to make sure you got the proper fusion machine. You got to make sure your trenching and shoring is. Steve and I are gonna talk a lot about trenching and shoring today because it is very imperative that you have a proper trench based off your soil conditions, whether you got a trench box, if you don't have a trench box, it's got to be sloped out there. It's got to be benched. However, you got to do it safely. We're getting too many calls nowadays of trench cave-ins, burying fusion equipment, burying people. Fusion equipment's replaceable, people are not. So make sure when you're doing in-ditch butt fusion that you're analyzing the situation. Stop and think about everything and make sure that you're setting the job up properly, because that's going to make the job in the end go way smoother. On the left here, you can see appears to me to be about a 24-inch line. I'm not sure exactly what it is. Trench looks safe. I could get on board with that trench all day. It is sloped out the proper way based on soil conditions. I'm assuming that it's a pretty stable soil. If it's not stable, you're going to have a much wider trench bottom there that you've got to pay attention to and make sure, because if it does cave off a little bit, I've seen it cave in and come to guys' feet. And it gets quite scary when people start scrambling that way.
Yeah, this is great because I mean, it goes to the constructability aspect, and that's true of any project. No matter what material you're using, you need to take a look at what do you have, what type of materials you're using, what type of equipment are you going to need or have on the job site, and how do I properly construct for that? I mean, you look at the picture on the left, because you got essentially, a 90 going in there with two pipe segments. Well, you can drop a fusion machine in there. You see that rather large 90 with pups on it that are already sized out properly. And as long as one side can move, that butt fusion machine will make that butt fusion. If you can't, there are alternatives for that as well, with different electrofusion couplings, mechanical couplings, whatever it might be. But as long as you take a look at the constructability as to which side you're going to fuse first, which side goes second, can I get in the ditch with this machine? Which normally you can, like I'll say you can. Chris will say, all right, you can, but it's going to take a lot of hoops for me to jump through. But it usually can be done. I mean, these guys are magicians with trying to figure it out and make it work.
This is a properly set up job site on the left-hand side. It's not in ditch. They're fusing mainline pipe. You can load that rack up and fuse pipe all day long and just drag it down the right of way. They're probably doing 500 to 1,000 foot sections that they'll come back in and fuse together later on. If this appears to be a gas project that we've got this picture on, but this was a water project, they'll fuse these 500 foot sections up and they'll pre-test them and chlorinate them right there above the surface. That way they know what's going on. Everything's pressure tested and ready to go. The one on the right is just another little simple in-ditch fusion where they're going to do a tie in there. So again, the question, in-ditch butt fusion, is it possible? It is 100% possible, given the proper condition. You have to make sure that you have enough room. That picture on the left where they've got trench boxes in there, trench boxes make it more difficult, but it makes it obtainable. You can't just throw a trench box in anywhere. You've gotta set everything up in the width of the trench box to be able to get that fusion machine down in there. If you can't get that jaw set down in there and swing the heater and the facer out of the way properly, it's going to create a nightmare in the end and a very unsafe work situation.
So we've seen several images here, fella. Sorry to interject there, Stephen.
Yep, you're good.
All of this equipment is designed to come off of the chassis and then come down into the excavation. All of the trench shoring and various levels. Now we're getting into increased complexity based on depth and based on width and things like that. They're designed not for the pipe, but they're designed to be able to give safe access for the people that are working around that excavation. And you'll see a lot of that through this. If we were just looking at pipe, you wouldn't have to have that wide of a ditch. So in an earlier video, we just showed someone putting a pipe or rolling a pipe over into a very narrow ditch through that process. But all of these that we're showing you are also safe for the people that are excavating it. We don't typically like to delve into OSHA that much, but we do really get into a lot of can we butt fuse in the excavation. And here we're walking through the whole steps. And like everything that we do, we've got to make sure that it's safe. And then also we're doing it properly. There's a lot of very bright people that have thought about the design of the equipment. And there's a lot of very bright people like Chris on that side that have figured out how to actually do that in the field to make what Stephen wants, or the other way, Stephen wants happen. So definitely
That's
keep
right.
going, guys. Absolutely.
Yeah, I think, and these are great examples because you don't, when you're designing these systems and you have, a narrow right of way and you're saying, oh, polyethylene won't work because I can't get that fusion machine down in the ditch. The whole fusion machine doesn't have to go in the ditch. When Chris is there, he'll say, man, it's really nice when it does, but they are designed segmented that way. So the collets and the gripping portion, heating portion can be lowered in separately. So when you're looking at the size that's needed, it's not the whole size of the fusion machine that has to go in there. It's just a portion of it. So just make sure that's taken into account when you're doing your construction aspect of the project.
Yeah, the picture of that fusion machine that's on the slide right now, I mean, you can break that down into a 3-jaw system where that's all you have in there, and it's just the width from the back of the jaw to the front of the jaw and the controls. That heater and that facer can set down in with an excavator or a piece of equipment and lower it down in the machine and take it back up out of the machine, and it can actually stay up out of the trench if need be. So if you got questions on that, a great, I mean, you can always reach out to us to get some dimensions of a fusion machine and actually how small you can be. But there's a lot of great resources out there. Macroy's website is amazing for stuff like that.
Yeah, I just want to make sure we pointed that out because I get those questions a lot. Here's a great example.
Back to the sloping situation here, it's imperative. I mean, there's no no better way when you're looking at this. I mean, that picture on the right, they're going on, looks like they're going under multiple utilities. They got multiple ladders to get out of the trench safely in different places. If something were to happen, they're lowering pipe in, they're going under utilities. Looks like they're gonna connect into this manhole at some point. The one on the left is rigging along with sloping. I'm gonna point out that the rigging is very imperative when it comes down to it, to make sure you have the proper rigging for the machine that you're doing. Because the worst thing that can happen is you drop that fusion machine or not support the fusion machine and you start breaking things, because it gets very expensive very quickly.
Good point.
So I'm gonna let Steven talk about the hydraulic trench shoring here, because I'm not real familiar on the hydraulic side, because I've never had to do that one.
I can also help some here too.
Yeah,
So,
jump in there, Alan.
yeah, you bet. So there's this is kind of slides that are set up to walk you through from a simple solution, which is the sloping, all the way up through the much more complicated, expensive slide rail system. For each of these excavations, the cost of excavation also jumps up in similar manner. So these hydraulic trench shoring systems basically operate against a plate, and then whoever's operating it pushes out a hydraulic piece in order to be able to expand that and to try to keep a simple and quick excavation from moving in that manner as well. Shielding is another next level up as we go through this. This could be a trench box that's all set up, and you simply move that into the excavation and put it down. Again, all of these are not for the pipe. They're all for safe access of the people working on the pipe, and their widths are determined in that manner to be able to provide us that. A lot of contractors will have these on site or renting any number of things. So one of the big things about polyethylene that Chris talked about was very long lengths. A lot of times we get segmental contractors that look at HDPE pipe and go, oh, but I can only install this amount at one time. And like, no, rent another trench box, rent yet another trench box. And that way you open it all up, you put in the high productivity of that 500 feet at one time, and then you cover it back up in order to be able to increase your productivity. You just use more rented trench boxes in that.
But
manner.
the point that I want to touch base on that with you, Alan, is people look at that and they're like, well, I need 500 feet of trench box. You don't need 500 feet of trench box. You need enough trench box to keep that trench safe, just in case somebody has to get down in that trench. So it may only be 1, 2, maybe 3 trench boxes. Obviously, the deeper it goes, the more expensive the trench boxes get, and the engineering and stuff like that. But that's a thing to keep in mind. You don't have to open up. You can open up all 500 feet of ditch, but you only have to keep enough of it safe at that point for the person to get down into that area to do what they have to do and then get back out. So you don't need 500 feet of trench boxes.
Absolutely.
Correct.
The allowable bending radius of HDPE will certainly allow you to move that pipe from above ground into place in much more easy fashion as well as we go through it. So I'll just kind of push through a couple of more examples of this as
Yeah.
we're looking at it. And this picture on the left shows a dewatering system as well through that process. So in high groundwater areas, we're going to have to make sure we lower that groundwater to be able to have a safe trench through that excavation process. And again, as Chris waded in there, a pun intended, with your last name there, Chris, you can easily put whatever you need in there and then move that trench box to the next spot as we're going through. And even with deep excavations, like you'll see through the manhole on the right here, there are trench systems available for you to be able to go through. Moving into a more expensive version for deeper excavations, now we have a slide rail system. Now, our dewatering system only works down to about 15 or 16 feet in most scenarios. You'd have to have a staged dewatering system to get even deeper than that if we have that much groundwater present and we need the bottom of that excavation to go through. But still, that's independent of the machines. That's independent of the HDPE pipe. Now we're talking about construction logistics that sometimes we think through or sometimes we don't as that design engineer moves in and creates Chris takes over the project to be able to go through and actually construct it. I'm moving us along a little bit here, fellas, because we
Yeah.
do have some other things to talk about. About 30 minutes left for everybody that's out there. We have great attendance and great keeping everybody here. Lots of great questions as well. So definitely absorb what we're talking about and send us all those questions as well. Here's a much more costly system for trench shoring, and that's a temporary sheet pile or a sheet system. And these simply are beat into the ground to provide that safe access for us as we go through. We often talk about a compressive fit slip lining or a pipe bursting process through the installation of a trenchless method of HDPE, and that soil interface from that machinery that we're using either for pipe bursting or compressive fit slip lining would push against a sheet pile like this. And then that sheet pile would provide that reinforcement to be able to resist the force from moving in that direction. But you could see also from the picture that they're really providing protection for the employees to access the actual work location to be able to move that through. These vary based upon how much work area is actually there, what needs to be protected is part of it, and can work in conjunction with other methods as well. As you'll see on the right here, there's a lot going on in that picture with sheet pile, sloping, and a few other things of that manner. So here's a little bit on open cut installation. So essentially, flexible pipes are considered to be ductile iron, PVC, and HDPE. Those are all installed in the same manner. They're all considered to be flexible, as to which they're working with the soil that surrounds that pipe to distribute the force loads to the soil surrounding it. Rigid pipes are a cast iron asbestos VCP. They're expected for that hoop strength to be strong enough to take any of the external loading and just go straight down to the bottom.
This is a great slide. I like that slide, Alan, because I get this question a lot: is people feel like polyethylene won't be able to withstand soil forces, and it's the exact same principles, exact same calculations as you would have for ductile iron or PVC work for polyethylene. Even with live loads, you have 2 or even 3 feet of soil cover, your live loads become very minimal, and you don't have to worry about it. And the other side is, if you have 25 feet deep burials, again, with a proper soil compaction and soil support, you don't have to worry about those either. So there's a broad range that you can use polyethylene in these situations. Don't be worried about it. All the calculations are there. Look at deflections. Because it is flexible, polyethylene doesn't have the strain limitations that some other materials would have either, before they become damaged or before they become compromised. So again, pretty broad range of installation conditions where you don't have to worry about it whatsoever. Now, the next slide you get into, I mean, this is one of my favorite things. So I absolutely hate comparing polyethylene to silly putty. It's really not the same thing, but it does give a good comparison of what we're talking about when we use the term viscoelastic. So if we've all played with a piece of silly putty over our lifetimes, maybe not so much now. In my day, you did. You've all played with it. You know that it's strain dependent, right? It's strain rate dependent, I guess I should say. So you take a piece of silly putty and you stretch it slowly. It just goes and goes and goes and deforms, and its elongation is huge. Conversely, you take it and you do a very high strain rate. It doesn't stretch much at all before it breaks. Very little deformation. That's the classical explanation of viscoelastic. So it's strain rate dependent on the different properties that it has. All of this has been defined for polyethylene. Very well understood, very well known. All the design calculations we use, whether it's long-term strength, short-term strength, burial pressure, cyclic fatigue, all of those things, that's all been factored into how this performs in that unique manner. And sometimes we can take advantage of it. Sometimes we have to use it as a negative and still account for it and properly design with it, and it works just fine.
So, as the opener for the video told us there, one of the users of this pipe material itself essentially just bends that in the field. And then that
Mhm.
force that's loaded obviously is going to put some type of if it's deforming, it's going to creep around of it. If it stays within the allowable bending radius, that's going to be just normal creep and no deformation, which what we're showing here is that. By the time that we've put that into the soil and allowed it to do the stress relaxation, that's going to be a perfectly happy pipe. When we're doing it in an open cut consideration like this, and we have that soil that supports that pipe, now it becomes a happy pipe. It's rested, it's relaxed, it's in its natural shape that it wants to be in that scenario. But it does take force to be able to put it around and put it into that bend radius that we allow for that pipeline itself. So this is just translating from that viscoelastic behavior that Stephen talked about, and we may very well just remove silly putty from everything that we have as far as the presentation is concerned.
I like the term happy pipe. We like
Happy
happy pipe.
pipe. So here's some terminology of the pipe embedment materials. Again, as I said earlier in the presentation, all of these things are actually involved even in the trenches, even in the complicated slide rail systems that you saw there as well. So we're providing that protection for the pipe. We've had some questions about concrete above it, things like that. Everything that you would do to protect an other pipe system, you can do as well to HDPE through this process. We do have design windows and tables for you. This came from M55, I believe, first version, to give us a generic design window of DR7 to 21 that you can have a max 25-foot cover according to this design window, 2 feet with no H20 loading. That's a box truck like the Penske, or 3 feet with that H20 loading. Just because this is the design window doesn't mean that something can't be done outside of that design window
Right.
itself. We just don't have to do any calculations if this is what we're looking at. So that's one of the simple things about installing HDPE in these normal parameters as we go through.
And you're right. I mean, that's going to cover probably 90% of your installation conditions that you're going to have with a water pipe, whether it's water transmission, force mains, sewer distribution, whatever it might be. These conditions are going to cover 90% of the time you're going to be looking at it. But if you're outside of this, then there are ways to design for that as well. But in other words, there's nothing unique you have to do. Same soil compaction, same backfill, same everything else you would for any other thing is going to work just like for polyethylene, just like it does any other flexible pipe.
And if you don't have a copy of the M55 manual, I would highly recommend you get one. And you should carry it around with you about everywhere, because somebody can ask a question and I guarantee you will find it in the M55 manual.
Very comprehensive, agreed. So you can see how narrow the trenches can be with polyethylene. They don't have to be extremely wide. With even up to 24-inch pipe, you're looking at the OD plus another 24 inches that's give you another foot on each side of the pipe, just to make sure you can get proper backfill and compaction, as Alan talked about earlier, with the different lifts and compaction and the different steps you go through. But you don't need a wide trench for polyethylene. There's nothing unique or special about it. In fact, many times you can use a much more narrow trench with polyethylene and be very successful. Dual trench is not uncommon. You can see 2 dual, I think these are probably 24-inch lines, probably for a force main, if I was to guess, or water transmission. And then in the picture in the center, you can see you can have complicated trench shapes. We've seen several examples of that already, where you can just bend the pipe into place or dig the trench the way you need to do it, fuse up the pipe, as Chris talked about earlier, and just drop it into place and bend it into that S-curve without a single fitting that's needed, and then just go back and do the compaction.
The thing that will change on that dual lay that he's talking about right there is the only time I've seen anything change on a dual lay is when the EPA gets involved and they want a certain distance between, if it's a sanitary sewer and a drinking water or potable water system, something to that effect. You may have to get a little wider trench than what you're seeing in this picture.
Correct. Yeah, you do have local regulations like that, depending on how you do it. Now, we have seen situations to where some allowances given for that with polyethylene because it is a fully fused system that has no joints. So because of that, there are some municipalities or states that will give an allowance to minimize that separation that's needed because you don't have to worry about leaky joints with a polyethylene system.
That brings up a great point because we just did a subdivision and they originally told us we had to have 12 feet between sanitary sewer and potable water. We actually got it down to where we could get as close as 6 feet, and they were perfectly comfortable with that after we showed the details of what was going on.
So I don't even have to come on here. You guys are addressing everything. I was so excited to try to add a comment, and Stephen just got it, and then Chris told the actual application of different things. I still think 6 feet's a little much for a fully butt fused joint that's self-restrained that's not going to leak. But hey, you know, you at least got them to back off some. We've got about 15 minutes left here, and then I know Stephen really wants to talk about surge quite a bit. So we're getting there.
Yes,
Thanks
I do,
everybody
Alan.
for being here, and the questions continue to roll in. So doing great, guys. Really good.
Yeah, let's get into surge just a little bit. Well, we'll talk about this. So, do you need, and I'll use this very carefully, do you need restraints? And then whether you need thrust restraints with polyethylene? And the answer is typically you do not, because it's a fused system that's fully restrained joints. You don't have to worry about pushing those joints apart with change of direction of flow as you would other materials. So 99% of the time, thrust blocks are not needed. Anchor blocks, yes. Thrust blocks, no. And we talked about ways you can anchor it. So Chris will put these in the ground in different ways and different combinations, but the theory is all there. The design is all there within the handbooks, that you can anchor it with different systems. You can have electrofusion flex restraints that are fused around the circumference of the pipe. Each flex restraint is what, Chris? Maybe I think it's 5,000 to 7,000 pounds of shear force.
Yeah, you're seeing roughly 700 to 7,500 pounds depending on the manufacturer now and how they embed the wiring on them. It's a great system, especially the bigger pipe. You don't have to make butt fusions in the field to try to put like a butt fused wall anchor or something to that effect.
Yeah, you can add as many of those as you need to give the proper restraint. I mean, on
But
small diameter
that
pipe.
is an engineered question too, based off of the manufacturer of the flex restraint. They will give you some engineering side to it, but it's always good to consult with an engineer like Stephen or Alan to figure out exactly how many of those you need for your system to keep anything from moving.
Correct. I mean, here's a great example. I mean, so you got polyethylene hooked up to a valve, which then transitions to an older PVC system. And you can see all they're doing is constructing a anchor block right there just to keep anything from moving. If it does, you can see that the angle that polyethylene's at and the way it's restrained, that's going to provide the majority of the restraint that's needed. But just as an extra belt and suspenders approach, for conservatism, you can then throw an anchor block in there with the proper rebar and design and cross-sectional area of that as well. Very simple done. MJ adapters, you gotta love them. These are great attributes. Now I'll let Chris talk about the actual field use of them, but there are fused on MJ adapters, which is what we're seeing here. My personal recommendation is that's what I would go with. There are fully mechanical MJs that you can use on polyethylene, just as you would ductile iron or PVC. Personally, that's not my first choice, and I think Chris could probably give some more real world examples about which ones he would rather see being called out and specified.
Well, my question to everybody is, why are you going to put in a completely leak-free system and then not put a butt fuse MJ adapter on the end of it? Why would you put a mechanical connection? So that's the first question of the whole situation. We install hundreds and hundreds and hundreds of these MJ adapters throughout the years of what's going on. And what you have there is, it's basically, I mean, you got your gland on there that's fixing to go into that valve with the ring. It bolts up just like a standard mechanical joint, but it's got that hub flange on there that ring slides up against. and it seals down just like you would with a mega lug on a piece of PVC going into that to restrain it. It's an amazing system, and Harvey Svetlik was kind of the wheelhouse behind that, from what I understand in all my years in the polyethylene business.
Yep.
These go by the hundreds. I mean, in all honesty, when you're doing a municipal water system, if you can talk them into MJ adapters rather than just mechanical mega lug system or something to that effect to ductile iron fittings, you're going to save yourself a lot of time and energy in the end.
Yeah, I mean, okay, theoretically they'll work. I mean, a good mega lug up to about 12-inch on polyethylene. I'm just giving you some experience with that. No problem. They can work fine. If that's what you got, that's what you need to use. It works extremely well. Even larger diameter sizes can work fine. There's just a little more nuances you're going to need to get it past. But you can do it, but you want to, like Chris said, you want to save yourself some headaches in the field. Use the MJ adapter that you butt fuse on, and then with the ring and bolts like you have here. It comes as a kit, very easy to order, very easy to specify, and to get it all in the field.
Well, and they make them two ways. I mean, this is great to connect to your legacy material, not just the valves. So you can connect to your legacy material with this. They make them in a male and female configuration, so you can go either go to the bell end of legacy material, or you can go to the spigot end of legacy material. I get calls weekly wanting to know, hey, how do we connect to this? And it's 95% of the time it's an MJ adapter.
Okay, so just a little bit of additional commentary on the two different types of fittings. An MJ adapter, as you saw there, is a robust molded fitting that we fuse right onto the side of the pipe as well, but it directly goes into whatever we're connecting it to. And then across these bolts, any type of movement or any type of force that connection is going to see transmits laterally across that. So a mega lug is different in the fact that we are now tightening something into the sides of that HDP or that fitting that we have, and it has to tighten into a stainless steel insert to be able to stop that creep from happening with the pipe itself. So the design of the MJ adapter is different based on who's making them. Some of them have stainless steel inserts, some of them don't, but that's up to the manufacturer that did it. But those are the two primary differences as to what happens for the direction of the forces between these two fittings. And I'm so glad you guys got into that as well. So we've got another 10 minutes for us here. If you want to talk about some tools that you could use for anchor block design.
Yeah, I mean, just jump in there real quick. So there was a new study done by the Plastics Pipe Institute about, I guess we see about 3 or 4 years ago now, which looked at, what is the standard anchor block sizing that's needed. And it turned out the older guidance on that was extremely conservative. I mean, it gave you this anchor block that was just prohibitively large sometimes. So Cornell University and some professors there did some studies on what we're looking at, using soil friction into taking that into account with movement, and then looking at, all right, what's the maximum amount of movement and force we're likely to see, and then resizing those anchor blocks to be more reasonable. That's all a new publication that's out there now for a few years. It is ingrained within the hdpeapp.com software I talked about before. So you can go in there and get some good information on the types of, the size of anchor blocks that's going to be needed. And then Chris, you just give it to him and he'll tell you how to install it in the field.
Absolutely. We just had a good question come in, Stephen. It says, can MJ adapters be molded into different sizes, reducers if you're connecting to PVC or ductile iron pipe that has a different OD? So most of the MJ adapters are actually designed, the hub of them are designed to go into ductile iron sized pipe. They do make them in IPS and they make them in ductile iron pipe size. So you can get them either direction, and you can also throw a reducer on there if you're going from, say, a 10-inch to a 8-inch or a 6-inch or something to that effect. You can get them that way. I just wanted to throw that out there instead of typing a big long answer.
Yeah, you get that question a lot too. Yeah, the transition between the two is very easily done. I don't want to spend too much time on this. I could spend an hour just talking about the long-term hydrostatic strength and the determination of it, but let's just, we'll simplify it a little bit. So this is what we call a stress regression curve. It looks very simple. It's really not. There's a lot going on here, but every thermoplastic material that's used in a pressure pipe application, and I'm talking about polyethylene, PVC, CPVC, cross-linked polyethylene, polyamide or nylon, all those go through this type of analysis, and an extremely long-term analysis to take the factors of creep into account, strain capability, and stress capability of the material, not just short term, but long term, to say, all right, what is the long term strength capability of this product when I make a pipe out of it, a pressure vessel out of it? How do I pressure rate this thing? So I'm not going to have to worry about pressure over the long term. Polyethylene, as we talked about earlier, all these properties are taken into account. There's multiple levels of margins of safety built into this at several different steps. So when we say that polyethylene has a 200 psi operating pressure allowance, there's a lot of safety factor already built in there. You can actually operate that system at 200 psi all day, every day in a gas and or a liquid environment. Not all materials are that way, though. You have to take different things into account. But for polyethylene, when it says 200 psi, PC 200 psi, it's 200 psi working pressure all day, every day. And we'll get into why that's important with the surge. Here's the equations you look at. So because of DR, we use a DR rating for this, dimensional ratio. It's a ratio of OD to wall thickness, or minimum manufactured wall thickness. So there's conservatism in there. And what's nice about that is it doesn't matter how large the pipe is, from 1-inch pipe to 65-inch pipe, that DR has that pressure rating. So a DR 17, as you see in the chart there, no matter how big the pipe is, will always have a PC 125 or a 125 psi operating pressure. DR 11, 200 psi. It is temperature dependent. So everything's designed for polyethylene to operate at 80 degrees C or less as our standard operating conditions. If it's above 80 degrees C on a continuous basis, not just like a little spike here and there for an hour or two and then it goes away. There are ways to reduce that pressure rating in a proper fashion all the way up to 140 degrees Fahrenheit of continuous operating temperature to apply that to the maximum operating pressure as you see in the table to the right there. So all these factors are there. All right, so what doesn't long-term strength take into account? It doesn't take surge into account. When we're doing the long-term stress regression, it's literally a pressure vessel. It's pressurized piece of pipe. It's static, and we see how much stress it can take over a certain period of time before it creeps and ruptures. So we got all that figured out for every thermoplastic material. But when you're flowing it, that's the whole purpose of a pipe. You don't want it to sit there and just hold fluid. It's a tank. When you're moving fluid, then you got a whole nother energy regime you have to deal with. That moving column of fluid is now going to generate energy depending on how fast it's moving. The surge effects. You can see the chart here. Here's one valve closure. It's not just one pressure transient that happens. You get a pressure spike. As that whole column of water has to stop, that energy has to go somewhere. You're taking kinetic energy, changing it into potential energy, and that's transferred into the wall of the pipe in the form of a circumferential stress. And you can see one valve enclosure could be several cycles. So we have to take that into account with the number of repetitive surges we're going to have and look at cyclic fatigue of the material. Go ahead. I know we're under short of time. So here's a great example. So we have pressure figured out. That's not a problem. But surge we got to take into account separately. So let's look at the three examples here. You got 10-inch pipe, polyethylene, PVC, ductile iron, and you have a pressure class related with each of those materials. First of all, pressure class is defined differently for every material and what it means. So just because you use a pressure class for one type of material for an application, the exact same application would take a different pressure class PVC and a different pressure class polyethylene. Design each one of them separately. Don't just take one and apply it across all. You won't get a good design. For example, DR17 polyethylene. It has a 125 psi operating pressure, but at 5 feet per second, that's going to generate a potential 56 psi in surge. Because of the modulus of the materials are different, that PVC, you're going to see a surge of 87 psi happen. And in ductile iron, you're going to see that same 5 feet per second velocity change generate 255 additional pounds of pressure over and above the working pressure rating. So what's that mean in a system? We talked about pressure class. The first columns on the right of this bar chart. The pressure class is essentially static. DR11 polyethylene, 200 psi. DR18 PVC, 235 psi. That's the pressure class. Okay, does that mean you can operate at 235 psi? Well, only until you start flowing the fluid. PVC does have a surge allowance for occasional surge. That means on a very limited basis over the life of the system, but not what they call a recurring surge. All the design manuals define it the same way. Recurring surge in, like, say, a force main application, it's recommended to take 55 surges per day over the life of the system. What's that going to happen? Now you look at all the way to the right on occasional surge, polyethylene can handle double its pressure class rating. PVC 1.6 times, and ductile iron has a flat 100 psi over the pressure class. So you can see now, even though you start with different pressure classes, they have to they design as the same pressure class in the long term when you have flow going on. You got to take that into account, or you're not going to get a proper design. Is that right,
So,
Alan?
absolutely. 55 cycles per day. That's that pump on, pump off, that type of thing. The occasional was 5 or 6, and that's all pumps on, all pumps off, or a firefighting event or something like that. I didn't even have to be here. I mean, you guys could just run the whole thing. It's fantastic through that. Love it. Real quick, we're going to talk just about that allowable bending radius, and again, what it does for us in the field. It makes Chris's job much easier. This is a utility conflict box for cast iron, a pipe that was going through stormwater. All he has to do is go around the backside of that and use that allowable bending radius to be able to make sure that we're not busting apart stormwater system to put in a new pipe in that manner. Here's some examples of that bending radius. I love this video on the right, and this will be one of the last things that we show. Of course, there's Dan Landy and Peter Dyke, who wasn't here to join us in that photograph. But this is a slip lining project in Tucson, and we are avoiding multiple bends within this line and allowing that viscoelastic behavior of HDPE to really shine. So we are forcibly pulling that through an existing pipe, putting it through a natural bend. We are not deforming it beyond yield to the point where we're breaking the material itself, but we are taking advantage of that viscoelastic behavior to make our lives easier in construction. How is this written on the specification and translated into the field? Those people that understand the properties of HDPE and can share these types of things with you understand how that's going to work between those two things. It's not always as easy as A is equal to this modified B or what have you, but this is effectively what using that HDPE material in the field shows. So we've been able to maintain most everybody through here, and we're done. We're getting to the contact info itself. Evan, I don't know if you want to come on and say a couple of things, but we are 1 minute over at this particular junction. You guys did great. I even could have taken a full back seat to this, and I love the fact that we've got exact experts to be able to share those experiences with us. Evan, you got a couple of closing remarks?
No, yeah, I just want to thank everyone for joining us and collaborating during this session. Reminder, if be the pipe, fabricated fittings, fusion equipment, any questions you might have, just reach out to SECOR and let us know how we can hopefully help you guys on the next job.
Chris, Steven?
Absolutely. No, SECOR is a great partner and a great resource. I hope you come away from this webinar with a little better understanding of polyethylene, and even more so, I hope it generates more questions, because polyethylene's been around as a piping material for 50, 60 years now. It's been used in a lot of different applications in a lot of different ways, and it can be a good solution for your project if you give it a chance and design with it properly.
Absolutely. Thank you, everybody, for coming out. And if you got any questions, feel free to reach out to any of us. The contact info is listed there. Take a screenshot of it and reach out to any of us. Dan Landy really likes to answer a lot of questions.
Thank you, everybody, very much. And here you go.
Thanks, guys.